All right, what is geometric algebra and can it help me? This is a talk I gave at PyData 2025 in Charlottesville, Virginia, but they lost the recording, so I'm re-recording it for YouTube. I'm also going to link to the slides below if you want to see those. All right, so do you even want to learn geometric algebra? So typical geometric algebras kind of look like this. You know, they're frustrated. They're trying to explain something to you and it's difficult, so hopefully this talk will, make it a little bit more accessible. All right, so to the point, what is geometric algebra? It's an object-oriented geometric language based on a non-commutative algebra, and that's Clifford algebra. Now, can it help me? So this talk was given to data scientists, so it's in that context, this question. So the answer is maybe if your problems are geometric, if your geometry is less than 10 dimensions or so, if you do a lot of physics in your domain, or if understanding math is useful. It's probably not going to help you out if you have really large geometries like 1,000-dimensional vectors or something, or if there's no geometric structure to your problems. And if you want to learn more, check out this website, byvector.net. This is where all the current geometric algebra stuff is being posted. And that's kind of the one slide summary for the whole talk. All right, so we kind of can motivate geometric algebra by this question. So I have two vectors, A and B, and I want to multiply them together. So what do I get? Now that's a really simple question, but it actually is still reoccurring even now. There's tons of posts on these Stack Exchange websites, and Freya Holmer, she made an entire video on YouTube about this. So it's kind of interesting that this question is still with us. So today I'm going to talk about Kingdon, which is a Python library, and this is a demonstration of how you would answer this question in Kingdon. In a two-dimensional algebra, we're going to make two vectors A and B, multiply them together, and we get this answer. So we're going to maybe unpack a little bit what this means. All right. So here's an outline of the talk. First, we're going to talk about who am I and what is Kingdon, this package. Then what is geometric algebra, how does it work? These are kind of brief overviews. And then finally, we're going to do a demo with Kingdon for a geodetic computation example. All right, who am I? My name is Alex Arsenovic. I studied at the University of Virginia. Did a PhD under Bobby Weichel studying microwaves. Then I started A10 Labs, a consulting company. Consulted for a few different companies. Worked for these guys. And during that time, I developed a couple open source modules. One was a module for radio frequency engineering, scikit-rf, and another one was Clifford. And I worked on this for a while, but I didn't create this. Clifford is a package for Clifford algebra or geometric algebra in Python, and it was originally created by Robert Kern, who is a NumPy dev. Then I took it over, and then these guys from Cambridge took it over, but then they graduated, got jobs, and Kingdon was kind of just hanging out, So enter Kingdon. So Kingdon is developed by Martin Rolfs, and it's a fresh implementation, and it's symbolically optimized. It leverages sparseness of the input, and it has really nice graphics thanks to Ganja.js, which is created by Stephen DeKinnick. And this enables a lot of visualization, which is super helpful. Probably most importantly, especially for this kind of audience, is that they have automatic broadcasting over the input types. So you can basically work with NumPy arrays of the geometric algebra objects or PyTorch tensors, and all the operators overload kind of as you would expect. And that's huge, and that's allows it to have a lot of performance gains. Here's some links specifically for Kingdon GitHub examples and a talk that Martin gave. So I would recommend checking those out. So what's geometric algebra? Okay, so David Heston who's kind of the modern architect of geometric algebra. He would say that it's a universal mathematical language for engineering and physics. And a response to that might be, okay, that sounds pretty great, so if it's so good, how come I haven't seen it until now? And the answer is that you probably have. You probably know a good amount of geometric algebra. So here are some examples of geometric algebras that most engineers or data scientists are familiar with. So the first one is obviously linear algebra, complex numbers, quaternions, dual numbers, vector algebras, and Poly-Dirac algebras. So those kind of get maybe more specific as you go down the list. But those are all, specific aspects or implementations of geometric algebras. So it's kind of been rediscovered many times in different scenarios. So Kingdon is one package that can implement all of those different algebras. So let's see it. So here's a complex, the product of two complex numbers. We get this result here. And this is how we would implement that in Kingdon. So we have an algebra of 2 dimensions, make these two multivectors, multiply them together, and you can just kind of quickly verify it. It's isomorphic. And given that this E12 squares to minus 1, it plays the role of I. Okay, dual numbers. These are used in automatic differentiation, and they're defined by the property that the number squares to 0. So this is how we can implement that in Kingdon using a algebra with one element that squares to 0, E0. And so this is how those are generally used. Here's just a demo using it with a polynomial. So quaternions, okay, product of two quaternions is this thing. It's a pretty long-winded expression. Here's how we can implement that with Kingdon. We have two multivectors, given components, and then here's just a side-by-side comparison. So you can see the IJKs are implemented with these other E12s, E23, E13s. If you're interested in quaternions or use quaternions, then I would recommend checking out this page. It's got a great talk on how to interpret quaternions with geometric algebra. Okay, so it can do these things. We've shown how we can implement that in Kingdon just kind of quickly. So how does geometric algebra work? The 10,000-foot overview. So you have to kind of expand your mind in terms of what objects you're going to deal with mathematically. So everyone's familiar with vectors, and you just have to basically take a vector and extend it into a plane. So here we have two vectors generating a thing called a bivector, which is an oriented plane segment. And then you can continue this process by taking the outer product of vectors to create higher order elements like a trivector, which is an oriented volume. And you can do that forever, so on and so forth. And this leads you to what I would call the pattern of geometry. So here shown on the left is the algebra dimension, and then shown on the right is the grade of the objects. And you can see, so for a given dimension, there's different counts of different grades of objects in the algebra. So in 3 dimensions, we would read this. There's 1 scalar, there's 3 vectors, there's 3 bivectors or 3 planes, and then 1 volume element. And you can see how this grows with dimension, which is kind of one of the scalability issues, for now anyway. All right, so how did we get there? So we use this outer product, and supposedly it generates these higher order elements. So kind of just coming from something we're familiar with, the inner product is usually given in this form, let's say for 2 vectors, A and B. And we can imagine just a dual quantity, which is given by A wedge B, and it doesn't return a scalar, it returns a bivector, which we're going to represent with a capital B. And we're going to interpret this thing as the parallelogram swept out by the vectors A and B. So you can imagine it this way. And just note that this is 0 when they're parallel, the 2 vectors, and it's maximized when they're perpendicular. And if we keep track of the orientation of this parallelogram, then this product becomes antisymmetric. Now this is kind of starting to jog your memory probably of the cross product, which is the outer product in 3 dimensions. So just let's go immediately to an application so we can see how we would use this. Here we have a system of equations, so there's some vector C, and we want to express that in terms of the vectors A and B, and we're trying to determine the amounts So the scalar multiples alpha and beta. So we can solve this in geometric algebra by wedging the whole equation on the left by A. That gives us this expression. Now, since the A's were parallel, they disappear, the outer product vanishes, and we're left with this. And then we can solve for beta as this ratio of these outer products. We can do the same thing with B on the right. That leaves us this expression. Again, the B's are obviously parallel because they're the same, and so those evaporate, and we can solve for alpha like so. And this is basically leads you to what's known as Cramer's rule, which is solving linear equations by ratios of determinants. And also, I should say, to be more precise, these ratios should be multiplicative inverses because the order matters. Okay, so now let's look at some trig. So here we have a similar setup where we have the vector expression of A plus B plus C equals 0, which is a triangle. So we can rearrange it a little bit, do the same thing. Wedge on the left by A, the A outer A disappears. Wedge on the right by B, B outer B disappears. We're left with this kind of triplet equation, and then we can re-express that in terms of the sine function and the angles. And this gives us the following triplet equation, which is the law of sines. All right, so the outer product is useful. We know the inner product is useful, and maybe we should consider combining these things. So if we abandon, that's spelled wrong, commutivity, and consider a dichotomy based on symmetry. So here's the product of two vectors A and B, and we've just broken this up by symmetry, then rearranged it, and this is necessarily true. So normally you would just imagine that the commutativity holds, and so the right term vanishes. But if we don't assume that, then we can associate that with the outer product, A wedge B. And this gives us the geometric product of just AB. They don't have any kind of symbol for it. And this is really the clutch idea that led to a lot of development. Okay, so that's kind of a 10,000 foot view of how GA works, what it kind of looks like in some simple applications. And now we want to look at, okay, let's solve an actual problem using this Python library and see what the code looks like. So this is an example for a geodetic computation converting between two coordinate frames. So one frame is ECEF, which stands for Earth-centered, Earth-fixed. And then we're going to convert that to a local coordinate system of east, north, up. So here's our Earth, and we're assuming a spherical Earth for this problem with some fixed coordinate system. That's our ECEF coordinate system. And we want to re-express some objects, some points, let's say, in this local coordinate system, which at some local tangent point A on Earth is defined by a locally north, east, north, and up frame. So it's just a three-dimensional coordinate system transformation is all we're doing. So I'm just going to show you how you can solve this with geometric algebra. You don't have to follow it, just want to give you a flavor for what it looks like. So here, for a sphere, it's obvious that the up direction is the same as our tangent point A. So we're just going to have to normalize that. Now, next I'm going to form this bivector, capital N, by wedging A with my north direction, E3. So this is a plane. Then I'm going to find the north direction by taking my tangent point A and rotating it 90 degrees in that plane. And that gives me my north direction, so lowercase n. And then finally I'm going to take the dual of that plane, which is created by wedging my north and up vector. Take the dual of that plane, so it's the vector perpendicular to that plane, and that gives me my east direction. So that's solved this way. Now this is the code that implements that in Kingdon. So it's pretty one-to-one, which is really nice. All right, so we're going to put this into a function. So we're going to compute the east, north, up frame at some tangent point A. And here's the code. I just showed it to you. It's the same thing. We're just going to return a normalized set triplet. Okay, now we want to basically we've computed this frame and now we want to project a whole bunch of points. Let's say we have a point cloud and we want to convert them from ECEF to this ENU coordinate frame. So this is a way to do that. We just have to basically, redefine the origin as A. So we're moving all the point B's, redefining their origin to A, and then projecting that onto a different coordinate system, which is our ENU frame at A. So that's the whole function there. But, since the vibe coding has come a long way, let's just compare what we would get using that method, right? Because this is a well-solved problem. It should be pretty accessible using those tools. So I gave GPT this prompt, right? Given a frame in ECEF, make a function to convert it to ENU. And, same with the tangent point. And this is what I got. And this is kind of standard. This is probably what you would get if you asked someone to implement this for you as well. And just comparing that to what we wrote down, clearly it's a lot simpler. It's less code to maintain. It's also more readable. A little bit of learning curve, but you're not stuck in the matrix and coordinate lands of all the trig functions. All right, but how fast is it? That's important, right? If we're doing millions of points or something. So we're going to compare 3 approaches in this kind of performance assessment of this specific example. The first one is a NumPy approach. So this is the code I just showed you that GPT generated. So we're going to generate a whole bunch of coordinates and then convert them. The second way is basically an iterated list way. So that's using the Kingdon functions I showed you without their internal broadcasting methods. So it's basically going to iterate through a list of the coordinates and apply the function to each one. And then the third method is a broadcasting method. So we basically generate take our coordinates and we generate a whole matrix of B's, and then we convert them all at once to ENU. So these just illustrate their 3 methods: the standard NumPy way, the iterated list way, and then this new kind of broadcasted approach that Kingdon allows us to do. And here's the performance. So here is our runtime on the y-axis versus our number of points on the x-axis in a log-log scale. And you can see the iterated list way, which is our orange line, is pretty slow. And that's probably about where Clifford was as well, the older library I worked on. But if we compare that to NumPy and the broadcasted Kingdon approach, you can see that you're not losing anything from using the new Kingdon approach. So for this specific example, the code is way more concise, it's totally geometrically interpretable, and it's as performant. All right, so that's basically the example. And in conclusion, so can I use this? So there's some pros, right? It subsumes a lot of different mathematical systems, so you don't have to convert between complex numbers and quaternions and matrices and vector calculus if that's something you have to do. It generates really concise code, right? It's got, it's a more sophisticated language, and that allows you to represent things more concisely. And it's getting more performant thanks to people like Stephen and Martin who are developing these libraries. There is a con, obviously. It takes time to learn a new language, and that's that's an expense. There's a dimensionality limitation based on around 10 dimensions currently, I would say. There's also a infrastructure limitations. So when you're actually solving problems in the real world, you're using a lot of tools that have been accumulated over time, and sometimes that infrastructure is not available in the geometric algebra currently. So that's a serious con. So here's just some links of interest I wanted to post. So this is a project. The first one is a machine learning project for transformers using geometric algebra. This is by some guys at Qualcomm. And then there's this fellow over at Collins Aerospace who's basically written a MATLAB toolbox and is trying to test it internally to see how it works. He gave a talk on that, which is pretty interesting. So bivector.net is where I would recommend you go if you're interested to learn more. They have a lot of different software packages, documentation, and there's a Discord if you need help, which is really good. And if you enjoy that website, you can support them with some merchandise. Like they have great hats like this to promote making algebra geometric again. And thank you for watching this if you made it this far, and I'll post links to these slides in the description, and thanks for watching. If you have any questions about this talk or anything, anyway, feel free to email me or leave a comment in the video section. All right.